Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 3-8 lesson on polynomial and rational inequalities. In this one, we will be figuring out how to solve and graph polynomials and rational inequalities in a single variable, and as a real-life application, we'll figure out when to sell a house. For the warm-up for this lesson, here are 5 expressions in the original inequality notation that we've been using. See how much you remember about writing these in interval notation. Pause the video, try that out. All right, let's see if we got the same thing. Now for this first one, we want everything between 1 and 6, including 6 but not including 1. So the way we would write that in interval notation, we would start with soft parentheses, or rounded parentheses, the first number. We always do a comma and then another number, this last number here. Since 6 is included, we're going to use a squared off bracket for that one. Next, for x less than or equal to 5, you always have to think about interval notation as, what are my numbers between? So this is everything to the left of 5. Now, if you're going left forever, then we can say that you're between negative infinity and positive 5. Infinities are always going to get rounded parentheses. This 5, since this is an equals here, we're including 5, we're going to use that bracket again. Now for this next one, we want everything between negative 8, except for negative 8, and also we want to go right forever. So we're going to do negative 8, rounded parentheses for that, comma, and since we're going right forever, we're going to do positive infinity. For this one, we want everything to the left of negative 3, so that's going to be negative infinity, comma, negative 3, both rounded parentheses. Now for or, we're going to signify this or with this little union sign here, and then we want negative 1 to 4, including negative 1, not including 4. And finally, all real numbers. This one's kind of tricky. You basically want everything from negative infinity to positive infinity, both soft or rounded parentheses. Before we go any further, I want to introduce a method we'll be using for this whole lesson called sign analysis. The basic strategy here is we're going to plug in x values to see where the function is either positive, y bigger than 0, or negative, y less than 0. Now, we're not just going to keep plugging in a bazillion x values. We're going to be very systematic about this. We're going to test around certain points called critical values. Critical values are x values where the function could change signs from positive to negative or vice versa. There are 2 big kinds of critical values we're going to be using. Looking at this graph, one of the ways you can change signs in terms of y values is if you have a root, an x-intercept, a 0. One way to change from positive to negative or vice versa is literally crossing through the x-axis. Another way to do it, if you either had a hole on the x-axis or you have one of these vertical asymptotes where you're flipping from one side to another, if you have any discontinuities, if you skip anything, it's at least possible to change signs. So we have to be careful here. All sign changes have to happen at one of these 2 types of things, roots or discontinuities, but not all critical values are going to give you a sign change. For example, in this graph, we have x-intercepts here, but since we're bouncing off the x-axis, we're not actually changing the sign of y. Or, if you have some discontinuities, in this one, notice we have a vertical asymptote and a hole, but neither of these results in a change from positive to negative, or the other way around. So we actually do have to test each of the intervals created by these discontinuities and roots. So our basic strategy for sign analysis then, we're going to test one x value before and after each of the critical values. We don't change signs between critical values, so we just need one x value in each interval, but we do need to test each interval created by critical values. So now that we've got kind of the theory out of the way, let's get going with doing an actual problem. For this one, we have the inequality 7x plus 28 is greater than or equal to 0. So we're basically trying to get a graph and also an interval of all the x values that make this true. So to start off with here, we're going to try and find out where our critical values are, specifically our roots. This is a polynomial, so we're not going to have any holes or asymptotes, but we can at least find the roots. Pause the video and take a moment to find the roots for this equation. All right, so there's a few ways to do this. You could pretend that this is an equals, subtract 28 and divide by 7. But I'm just going to kind of get us in the habit of factoring here. So I notice that I can factor a common factor of 7 out of both of these terms, leaving me with an x plus 4 inside. So that means that we're going to have an x value of -4 for the roots. Now that we've got this, what are we going to do with it? Well, we're going to go ahead and graph this root and shade the correct region. And you've probably done this before without the sign analysis that I'm about to show you here, but what I'm going to show you will work on any inequality, not just one of these linear ones. So let me do a number line here. And I'm not going to actually put in hash marks or label every single spot on here. I'm only going to put the spots on that have critical values. So -4 is my only critical value. I will put that on my number line. And now I need to figure out what type of dot is going to go with it. So there's two types of dots you might remember, the open dots and the solid dots. And which one you're going to use is going to depend both on your inequality and also on what type of critical value. For discontinuities, which we're not going to see for a little while, since the function does not actually exist there, for discontinuities we're always going to use an open dot to show that whatever that critical value is not going to be part of our solution. But for just plain old roots, like the one we've got here, we're going to use the inequality to figure out whether we have solid or open dots. Just to review, if you have the equals under here, that means this critical value is going to be part of your solution. So you're going to use a solid dot to show that on your graph. And if you don't have the equals, then we're going to use an open dot to show it's just kind of a fence, a place marker that's not actually part of the solution. So here we have the equals. That means we're going to use a solid dot here. All right. At this point, we need to figure out whether we want to shade the stuff to the left or the right. And again, if you had already solved this and gotten x by itself, there's a way to quickly tell which way it's going, but that only works with linear inequalities. So what I'm doing here is something called sign analysis. We're going to start by picking an easy number in each of these intervals and testing it out in our inequality to see if it makes the inequality true or false. So easy number, something to the left of -4. So there's a lot of options. I'm just going to go with -5. It's the closest number to the left. You could have done -1 million if you wanted to, though. Anything over here should work. And then we're going to go ahead and plug it in. Now, when you're plugging it in, I do recommend that you plug it into the factored version of your inequality, which is kind of why I factored this instead of doing it the other way that we already know how to do. And then just using sign rules, multiplying and dividing sign rules. So, for example, if I do 7 times -5 plus 4 and analyze the signs here, 7, now I'm looking at the signs of each factor, each thing that's being multiplied. 7 is a positive, and that's always going to be positive. But -5 plus 4, that comes out to a negative. Now, notice that I don't really care what specifically this comes out to. I'm just looking at the sign. So that's going to make this go a little bit faster. And when I'm doing my sign rules, you might know just off the top of your head that a positive times a negative is a negative, but we're going to see problems where there's lots more positives and negatives kind of flying around. So an easier way to do this with a lot more terms is to just count the negatives. And if you have an odd number of negatives, then you're always going to get a negative result. An even number of negatives, like a negative times a negative, that's always going to give you a positive. Here we have an odd number of negatives, just 1. So that's going to come out negative as the overall result. So I'm going to write negative next to my number line above the number I tested here. And it's up to you whether you want to write down the numbers you're actually plugging in or you just want to put the signs up here. The bare minimum, though, is you need the sign up here. You don't need all this other analysis out here. I'm just showing that so that you can see where I'm getting this from. All right, pause the video and see if you can figure out the signage over here on the right side of -4. All right, so which number did you pick to plug in there? Again, lots of options. You could do -3. That wouldn't have been a bad one to pick. However, I went with an even easier number. I like to use 0 whenever I possibly can. 0 is very easy to plug in. So plugging that into my expression, I'm looking at 7 times 0 plus 4. And again, you don't have to write this. I'm just writing this to show you where I'm coming from. Analyzing my signs, this is a positive times a positive, which is going to come out positive, greater than 0. So I'm going to write a plus right here. Now that I've got each of these intervals labeled as positive or negative, I am going to figure out which ones I'm shading. I'm either going to shade all the negatives or all the positives. To figure that out, I'm going to go back and use my inequality one more time, this time to decide between positives and negatives. Since we're writing greater than 0 right here, or greater than or equal to, that means I want the positives. If this had been a less than, I would have wanted all the negatives. Since I want all the positives, I just look at anything with a plus, and I'm going to shade that interval. Now that we've done that, we're also going to write the solution set in interval notation. And this is very easy to do if you've already got the graph. This is why I recommend you do the graph before this next part. We're just going to use the graph to write our inequality in interval notation. So pause the video and take a moment to do that, just to get practice with this. All right, so we're going from -4 to infinity here. We're going to have a bracket on -4 because we have a solid dot. That's part of the solution. And infinity always has to get a rounded parentheses. So there's our final answer for this one. Here's another example. This time around we have a quadratic inequality. This is not something you would be able to do by just getting x by itself, like you're used to doing back in the day. So we really need the sign analysis this time around. Pause the video and see if you can find the critical values to start us off here. All right. So I see here that this expression looks factorable. So again, with critical values, I'm trying to figure out what values will zero this thing out. So let me start by factoring it. Two things that multiply to 20 and add up to -12. It looks like, let me see, we got 1 and 20, 2 and 10, 2 and 10, -2, -10. So x minus 2 and x minus 10. Excellent. Now for my roots, whatever zeroes each of these parentheses out, I'm going to have a 2 and a 10. All right, so these are what I'm going to have to go ahead and put on my number line. Go ahead if you feel confident and pause the video, put these on your number line, do your sign analysis, and see if you can come up with the graph and the interval at the end. Feel free to stop and play the video at any time to kind of catch you up and make sure you're going along this correctly. All right, so got my number line here. Now I have to decide between solid and open dots. Since my inequality has no equals, these are both going to be open dots, even though they're roots. So I have an open dot on 2 and an open dot on 10. Now I'm going to pick something from each of these 1, 2, 3 intervals. Over here on the left, an easy number over here would be 0. So let me plug 0 in. And I'm just going to show this one more time just for this one interval so you can get a sense of what's going on in my head when I do this. So that's going to be a 0 minus 2 and 0 minus 10. Again, going on in my head here. So 0 minus 2 is a negative. 0 minus 10 is a negative. I know what negatives they are. I don't really care, though, just the fact that they're negative. Counting the negatives, we've got 2 negatives. That gives me a positive, so I'll write a plus there. And now I move on to the next interval. I need a number between 2 and 10. I'm going to go ahead with 5. 3 would have worked. 9 would have worked. Anything else in there? So 5 minus 2 is going to be a positive. 5 minus 10 is a negative. That's a single negative giving me a negative result. Finally, something to the right of 10. Let's go with 11. 11 minus 2 and 11 minus 10 are both going to be positives, so that whole thing is coming out positive. Next, which of these did I actually want? Looking at my inequality in the beginning, this is greater than 0. That means I want the positives. So I have this positive interval over here to the left of 2, and this positive interval to the right of 10. And to capture both of those intervals in interval notation, I need to go from -2 to 2, normal parentheses for both of those because I've got infinity and an open dot. And I'm going to have to do my little union symbol, that little U, and also include this interval from 10 to infinity, also with rounded parentheses. For this next example, we're not going to make you go to the trouble of factoring. This one is more about the sign analysis. So quickly come up with your roots, plot those out, and do some sign analysis to see what you come up with. Give it a try. All right, so our roots here, this is already factored, so we're just looking at what zeros out each parentheses. So that would be 1 for that first one, and then 3, and then 5. Setting up our number line, These are all roots, but again, the inequality has no equals, so these are all going to be open dots because none of these are actually, we don't want anything that makes this equal 0, just things that make it less than 0. So we've got 1, 3, and 5 open dots. And let me check out some numbers in each of these. Now we have 4 different intervals, so it's growing here. Let me try 0 to the left of 1. And a little trick that you can use sometimes, if you have a squared factor or just an even power factor like this x minus 5 squared, it doesn't really matter whether it initially comes out positive or negative for whatever you plug in here. When you square something, you're always going to multiply something by itself. So you're always getting a positive whenever you square something. So in general, factors with even powers always come out positive, and for that reason, since that's not going to affect the number of negatives that you're involving in the problem, you can actually just ignore those factors during sign analysis because it's always going to come out positive. We only really care if something comes out negative, and then we count the negatives. So when I'm doing my sign analysis, I'm not even looking at this x minus 5 squared. I am just looking at these first 2 factors that are not squared. So 1 minus 0 is going to be a positive. 0 minus 3 is going to be a negative. Positive, negative is going to give me a negative result. Next, a number between 1 and 3. I think 2 sounds good. So 1 minus 2 is a negative. 2 minus 3 is also a negative. Even number of negatives gives me a positive. Next, between 3 and 5, I've got 4. 1 minus 4 is negative. 4 minus 3 is positive. Odd number of negatives gives me a negative. And finally, we'll do 5 after 5. Let's do 6. So you might be thinking that there's a pattern here. So far, it's always been switching between negatives and positives. Let's see what happens here. So we have 1 minus 6 is negative. 6 minus 3 is positive. So 1 negative, that gives us a negative result. It did not switch this time. So you always have to check. You can't assume that you're just flipping back and forth. Now, did we want the negatives or positives? We said less than 0 for the original inequality, so that's the negatives. So that's everything over to the left here. We also have this interval between 3 and 5, and we have the interval after 5 here that we're going to include as well. Now, be careful when you're writing out the intervals here. So we have negative infinity to 1 with parentheses. We have a union, and you might be tempted to just write 3 to infinity, but this 5 is not actually part of the solution. So we have to leave it out. We have to do an interval from 3 to 5 with parentheses, and another interval from 5 to infinity, again with parentheses. For this problem, for the first time, we're dealing with a rational inequality instead of just a polynomial. So we have this fraction greater than or equal to 0. So we're looking for values that make this whole thing positive or 0. And we're going to start by finding critical values, just like we did before. The game changer this time around is that in addition to things that zero out the function, the roots, we also have discontinuities, things that make this undefined. So to find those, we're trying to figure out things that zero out the numerator, those will be our roots, and things that zero out the denominator. Those will be our discontinuities that give us wholes and asymptotes depending on what else is going on. So pause the video and see if you can come up with the critical values for this. All right, let's see how you did. So let's go ahead and factor everything. That's the easiest way to figure out what zeros things out. In the numerator, I need 2 numbers that multiply to 4 and add up to 4. That would be positive 2 and positive 2. So I can write n plus 2 squared if I want. And then down here, I can actually take out a common factor of n, leaving me with an n plus 4. Now I'm going to write out my critical values. Now I'm going to do the discontinuities first. The reason I'm going to write those first, every now and then I'm going to have critical values that are repeated in the numerator and denominator. So I don't want to accidentally list something that would have been a whole as one of my roots. I want to know that it's a discontinuity. So let me get my discontinuities. I've got one at 0 for this n. That zeroes everything out. And also negative 4 will zero out this factor right here. Those are my discontinuities. And now looking at the numerator, I've got negative 2 zeroing out this factor, and it's a repeated factor. So I guess I have a duplicate root of negative 2 that I don't really need to write. Okay, we've got our roots, we've got our discontinuities. These will all have to go on our number line, and we will have to test the intervals around these. So pause the video and see if you can take it the rest of the way here. And just a little hint as you're doing this, if you have a single point that you need to include in your interval at the very end, you can use these curly braces here around just that one number. All right, give it a shot. All right, so let's go ahead now. So I've got a number line, and I'm going to put on my critical values. So the furthest left one is going to be this -4. Since it is a discontinuity, it automatically has to be an open dot. There's no choice on that. The next one, as I move further to the right, is this -2. Since this is a root, this could be an open or solid dot. Looking at the inequality right here, we have the equals on our inequality, so roots then are going to be solid dots on this particular problem. Again, that's not always the case. Roots can be open dots if you don't have the equals here, but since we have the equals, this has to be solid. Moving on, we have 0. That's our final critical value. That's a discontinuity, so that's an open dot. Now I'm going to go ahead and do my sign analysis around these. And the good news is when I'm doing this sign analysis, even though there's a fraction involved, for sign analysis on rational functions, I'm still just counting the negatives. As long as this is in factored form, I can just count the negatives. Because multiplying or dividing, it's all the same sign rules. Odd number of negatives is negative, even number of negatives is a positive. So choosing a number to the left of -4, I've got -5, seems to work out pretty well. Now, we can also be a little bit crafty on this. You'll notice that since we have this squared factor in the numerator here, this is always going to come out positive. So I can completely ignore this n+2 squared when I'm sign analyzing my numbers, if that's a word. So I'm really just checking out my denominator that has the non-squared factors. So we have a -5, that's a negative, and then a -5 plus 4 also comes out negative. 2 negatives gives me a positive for this interval. Next, between -4 and -2, let me try -3. So I have a negative, and then a -3 plus 4, that's a positive. So a negative positive gives me a negative. Next, between -2 and 0, let me do -1. That's a negative out here, and a positive inside, -1 plus 4. Negative positive gives me a negative. And then finally, we have something bigger than 0. I think 1 is an easy enough number. So that's going to be a positive times a positive, coming out positive. Now we wanted greater than or equal to 0. So that's going to be all the positive intervals. So we have an interval to the left of -4. We also have an interval to the right of 0. And writing out my solution set, I've got -infinity, comma, -4 with parentheses because we have an open dot there. And now this -2, it got a solid dot, so that means it actually is part of our solution. Since it's just its own sort of point, its own little island of insanity there, we're going to use these curly braces for it. So we're going to do union curly braces -2, and that's telling us we just have -2, not an interval really. And finally, we have everything to the right of 0, so 0, comma, infinity with parentheses. For our last example, we'll throw a little real-life problem in here. Let's say we want to figure out when the profitability of a housing market is negative based off of this proposed rational function to represent the market. So maybe they came up with this by looking at a whole bunch of data and sort of turning it into a prediction curve of some kind. So pause the video and let's start by finding critical values here. All right, let's see how that worked out. So the numerator, there's a lot going on there. We have a 4th power. This one, if you look carefully, is in quadratic form. We have x to the 4th, x squared, and a constant. So let's think about if there's two numbers that multiply to 225 and add up to -34. So they would have to both be negative to multiply to a positive and add to a negative. 1 and 225 is not going to do it. 3 and 75 won't work. 5 and 45 is the next one. We're getting closer. That would add up to -50. Let me think. Does 7 go into that? Not really sure. I know 9 does, though, because the digits in 225 add up to 9. So 9 times 25 multiplies to 225 and adds up to 34. So I'm going to split this up as x squared minus 9 and x squared minus 25. And factoring a little bit further now, We'll do the numerator first, and then I'll take care of the denominator. So this x squared minus 9, we can split that up using square rooting. So that'll be x plus 3 and x minus 3. We can do the same thing with the x squared minus 25, so x plus 5 and x minus 5. And then down here we need two things that multiply to negative 15 and add up to negative 2. That would be, let me think here, positive 3, negative 5, so x plus 3, and x minus 5. So we have a whole bunch of factors here. Now, when I'm finding critical values, I'm going to write my discontinuities first before canceling out so that I don't lose track of them. So looking immediately in the denominator, I see I've got discontinuities at negative 3 and 5. And then I'm going to find my roots and do the sign analysis after I cancel out. So the x plus 3's, it looks like, can cancel, along with the x minus 5's. And I'm just going to rewrite this and clean it up a bit. So that leaves me with x minus 3, x plus 5, all of that less than 0. Now with that, I can find my roots. That's going to be positive 3 and negative 5. Notice the roots are the things that zero this out after I cancel out common factors. All right, so let's go ahead now and actually go ahead and pause the video and see if you can do the sign analysis based off of this. All right, let's take a look. So we've got our number line here going from left to right. I've got a root at negative 5. And because I have no equals in my inequality, that's going to be an open dot. And next we have negative 3. That's a discontinuity, automatically open. After that we have positive 3. All the roots are going to be open dots because there's no equals. And finally, discontinuity at 5. Doing some sign analysis. Let's see, we've got negative 6 to represent that out there. And the beauty of this, now that I've canceled out all this crazy stuff, I don't have to plug negative 6 into 6 different places. I've just got these two places here in the simplified expression. So I'm going to have a negative and a negative gives me a positive. Plugging in negative 4 now between negative 5 and negative 3. That's going to be a negative and a positive giving me a negative. Between negative 3 and 3, I've got 0. So that's going to be, let's see here, a negative and a positive gives me another negative. Between 3 and 5, I've got 4. That's going to be a positive and then another positive, so positive. And after that, after 5, I've got 6. That's going to be positive, positive, so it comes out positive. And I wanted all the things that were less than 0. So that's this interval, the second interval right here, and this third interval. Writing out my solution set, I've got negative 5 to negative 3 with parentheses. And again, I have to leave this negative 3 out. It's an open dot. So I've got negative 3 to 3, more parentheses, and a little union to keep everything together. So that's going to wrap things up for this one. Till next time, Mr. Sutton, signing off.